So let's move on to Karl. So Karl Guttag is the Chief Science Officer at Raven, and he's an expert in AR displays and optics. And he's going to break down some of the factors driving display and optic selection in AR headsets, and how those factor into design. So Karl, if you go ahead and take it away.
Yep. Hi there. Well, let's see if we can get the screen go. Hope you can see the screen now. Yep. Well, we're going to try to give a quick topic, went through the topic and all, and I ended up keep adding slides to this. So it's going to be a fast moving overview of the subject. So I'm just going to hit a few high points per slide and go with it. Let's see. Done. There we go. Real quickly on my background, I was an IC designer, came out of university, studied electrical engineering. I was 20 years with Texas Instruments. I was the youngest fellow in the history of the company. After 20 years with TI, I went out in the startup world and started getting involved in display devices. I've been in 4 display-related startups in the last 20 years. So I've had 20 years, kind of 2 careers. One career in the large company world working on silicon, and the last 20 years working on mostly display devices for about the first 10 of the next 20. And then the last 10 years, give or take, I've been mostly focused on more system level products using displays. So I also do a little intellectual property consulting on the side. I have 150 US patents. I've been involved heavily in graphics. So most of my career at TI, I was working on pixels and graphics devices. I'm probably best known today for my blog, KGOnTech.com. And it's often said about my blog that we love, and this is actually a quote from somebody who came up to me at a conference, we love your blog when it's not about us. I tend to be very analytical and critical of what's going on. So I've been around the industry over 40 years, so I've kind of seen it all and done it all. I'm going to start with just a few basics. You know, we all, basically every thing I ever see always seems to start with Ray-Ban sunglasses and ends up looking like HoloLens. When we talk about the images we see, oftentimes people publish their ideal images or computer-generated images, or in the case, this is a HoloLens 2 camera feed. This is what it actually looks like. I believe my blog has posted some of the best and most accurate pictures ever taken of the HoloLens, at least ones published publicly. So I go to great lengths to try to get something that looks very much like what the eye sees. So this is kind of what you see on your camera feed on the left, and this is what your eye sees on the right. So there's quite a bit of disparagence there. Basically, AR is a very hard thing to do. We're trying to do more or less 3 main things. We're trying to combine, the display device is often small and too close to the eye for you to see well. So we're trying to combine that. We're trying to change the focus of the display device so when it's presented to the eye, it's in focus because it's actually too close to the eye for it to be in focus. The second thing we've got to do is we've got to combine the real world. And this is the really hard problem, that in this, whatever we do for combining optics, and this is meant to be very generic, it's going to have some bad effect on the real world and some bad effect on the display. So all optics do some level of damage to the real world and the virtual image, either dimming, distorting, polarization, or diffraction, and all kinds of other things. I'm not going to go through all these, but these are kind of my 23 deadly sins, or list of 20, the kind of a matrix of problems to solve. They go for everything from transparency to brightness, contrast to cost to power to weight. I oftentimes say, and oftentimes when you try to fix one of these things, you have a negative effect on other things. I usually say this is solving an n-dimensional chess problem. There's just so many different factors. And this is one of the reasons why what is it? Google Glass came out, what, 2013, I guess. So 7 years later, still trying to get there. One of the things people worry about a lot is transmissivity. This is particularly important in social factors. People want to see the other person's eyes, but also you want to be able to see the real world. There's quite a variety in what people call augmented reality. And by the way, I'm almost exclusively talking about augmented reality today. And within that, I'm talking about optical augmented reality, i.e. where you look through some kind of transparent thing. So we go for everything from almost 85%. Magic Leap was only 15% transmissive. And then in between, you have the Nreals and other stuff that are in the 30 to 40% range. Very simple optical concept. Most simple optics don't do much in the way of magnification. The way that we magnify is we actually move the eye closer to the screen and then use the lens to focus. So the main function of that lens can be thought of as to function the image, to focus the image. What I did here real quickly is I took a camera that simulates the eye pretty well, at least for this purpose. Put it about the distance, put it at the distance the eye would be from the camera, the distance the eye would be from an iPhone. This is for a little VR adapter. And I take the picture at this location, then I remove the headset, take the picture from the same location, and nominally magnification is measured at 25 centimeters or 250 millimeters. Well, if I do that, we find that about the image is going to be magnified through that headset by about 5x, but about 3.5x of that comes from the fact that the camera's been moved closer to the screen. So really about 70% of the magnification is due to moving it to the screen. The lens is not making the image bigger. This becomes important because if we start with a small display, the easiest way to make it bigger is to move that display much closer to the eye. So why is AR so difficult? Well, AR is not just a little harder than VR, it's a lot harder. Optical AR is very, very hard. Part of the problem is where we want to put the display is right in front of the eye, but if we do that, we block your vision. So VR get to take the prime position. They also got to use a cheap flat panel display and block off all your vision, so that they can use some fairly simple optics to correct. Whereas with AR, we have to somehow take a small display and make a big image out of it, which, going back to the prior slide, is very difficult. And so we've got to route it to the eye, and we have to combine what's in the real world with what the eye sees. And on top of all this, when we build these little tiny displays, many of the pixels are only small integers of wavelengths of light. Another basic principle is light goes in straight lines unless acted upon, unless it goes through a medium. So if we look at light rays, if I want to illuminate one corner of the eye, I have to have a light ray coming from that position at that angle. So if we move the optics further from the eye, like we don't go right in front of it, but as we move out from the eye, the optics have to get forever bigger. So this becomes an issue. We also have to illuminate, and this is another concept people talk about, is the eye box. Basically what that means is how much can your eye move? If your eye moves, can you still see the image? So another way to look at an eye box is to say, look, if I was looking in a mirror, a small mirror, and looked at something in the mirror, if I move my head, it immediately starts cutting off. You've basically got a small eye box. Now, if we made a bigger mirror, then you could move your head and still see the whole image a little bit, move your eye a little bit. Another way around this problem is to do what they call pupil replication. These are pupil replicating waveguides. Probably the easiest to understand is a Loomis light with partial mirrors. And what they do is they take the image and have a partial mirror. Each of these is like 10% nominally. Loomis actually uses less than that, but I did this for the simple example. So what we did is each mirror is a little more reflective. So wherever the eye is, it actually ends up seeing the same image. Note this, each of these mirrors has the entire image, not just a fraction of it. Let's see. So diffractive pupil replication, which is more common, such as the HoloLens 2 and probably half a dozen to a dozen companies now, it also uses pupil replication, but on a more microscopic level. We'll just leave it at that. The other big thing to get here is another thing I'll talk a lot about is nits. And if you don't know what nits are, they're basically a measurement of brightness of light coming into your eye, very simply put. So if we look at all the light that comes out, and one of the easiest ways to think about it is to say, well, if I had a stream of water, and let's say these two streams on the right were coming out at the same amount of gallons per minute. So the same amount of water is coming out. But in one case, if I put my hand in front of this in a tight stream, it's going to come out very with high pressure or high force. And in this other stream, it's going to be all over the place, but at a much more diffuse force. So this is what we call, so for the same amount of light, we get lower nits if we spray it out all over the place. So in our case with near eye displays, what counts is what meets the eye. Turns out that this kind of light is really good for like a computer monitor where your head's going to be moving all over the place. But when you want to use something like AR, you want the light to be highly compacted. By the way, for the point of reference, a cell phone's about 500 nits. A computer monitor is somewhere between 100 to 200 nits. But if you go outside and you're going to wear your AR headset, if you're looking at concrete has about 10,000 nits. So there's a lot of light out in the real world when the sun's out. I won't spend too much on this other than to bring up this concept of étendue. What étendue basically says is if you collimate light, try to make it come in straight, or you shrink the image size. You can do one or the other, but you can't do both. As you try to make the light collimated or moving in very parallel straight paths, you have to make the path of the light bigger. If you try to reduce the size of the light path to a smaller image, and this is what we got to do when we enter into these pupil replicating waveguides, well, now all of a sudden the light's not collimated. So effectively what ends up happening is you take your fan sprayed out light that you're doing to collimate it and running it into a funnel. So very little light gets through. Now, you'll hear about people using micro lenses, arrays, and whatnot on top of things like micro LEDs. And what they're trying to do is collimate down at the pixel level. Because once you have the entire display, you can't collimate you can collimate the image, but you can't straighten out the light rays. You have to do that right as the light rays are coming out. This is this concept of étendue. Étendue basically says that for a given area of light, the product of the angular diversity to rays is always getting worse. So one of the big things we see out here are pupil expanding waveguides. People like pupil expanding waveguides because they're thin. The problem with pupil expanding waveguides is they're very inefficient. This idea of kind of funnel the light into it, we can lose about 50x of the light. So only 1/50 of the light from most display from like an OLED or micro LED can make it into the typical waveguide. You lose another 50x because we're going to take the little bit of light that makes it in, do that étendue, and we're then going to immediately turn around and spread it out over the entire exit area. So we're going to expand the image back out. This has the advantage of making the projector small, which is a good thing. We want the projector to be small and lightweight, but it means that it's very, very, very inefficient. When we net this all out, we could get about 1/5000th of the nits in to nits out. So that's a huge loss. So even when you hear about things having thousands of nits, well, if you start with 1,000 nits in, you're going to get less than 1 nit out, which has been the big killer for trying to use these with, say, OLEDs. even if you had a bright enough light source, there's still issues of battery, heat management, and weight issues. One factor in this is one of the big factors why you're seeing people look at, it's causing people to look at laser scanning more. Laser scanning does not have the severity of this input collimation issue. So we've already talked a bit about diffractive waveguides. The most famous one these days is HoloLens and HoloLens 1 and 2, but it's been used in a myriad of products, Wave Optics, DispelX, Magic Leap. They all use diffractive waveguides. DigiLens, another company out there doing it. So there's many manufacturers. You get a large eye box, you can get a pretty large field of view. There are actually people getting field of views even greater than 60, going up to 70 and 80 degrees. It's thin. That's the good side. The bad side, poor efficiency, poor image quality, lots of, and I'll talk a little more about that later. And you get waveguide glow, or really what I call front projection, and you get very poor uniformity. So the image quality is not there. There's a slightly different technique used by reflective waveguides, or reflective pupil expanding waveguides, really. A company called Loomis does a lot of that. And it's thin. It has all the same advantages. It has actually quite a bit better image quality in every test I've ever run on it. But there's only a few manufacturers, and the issue has been getting cost. Now, the company Loomis is working to try to improve that. They just did a new deal and a new announcement with Schott, and they've got this really small and enticing model that they're just developed with Schott. So we'll see how that works out. One thing about these, they've been able to get like over 4,000 nits out of these waveguides, whereas something like the HoloLens is only about at 500 nits. 500 nits really isn't enough for outdoor use without needing really dark sunglasses in front of it. Whereas at 4,000 nits, you're starting to talk more of an outdoor product, or ability to use it outdoor. So I won't go too much into this here. One of the biggest points I like to make on this slide, though, is that the orders. What happens, the way a diffractive waveguide works, if you don't remember your fixes, it didn't have it, is basically it bends wavelengths. When you go through a grading process, either reflective or transmissive, light will get bent as these gratings approach the wavelength of light. Light will get bent, and it gets bent kind of like a prism. It gets separated into various orders. Now, the good news is that allows them to bend the light and bend it in fairly small spaces. The bad news is there's these wasted orders. One of the biggest things you see coming all the time with these things is called waveguide glow. And what happens is they're projecting half of the light. As much light comes out at you as goes towards your eye. That's why when the guy looks at you the wrong way with these, you get this glowing eyes effect. Not very flattering. By the way, one thing I'll point out, I've used several images here from a book by Bernard Kress. He's written an excellent book available on SPIE, Optical Architectures for VR, AR, VR, MR headsets. And that's by Bernard Kress. It's an excellent book, just compendium of good information. Okay, so for this one, I wanted to compare, this is a slide comparing HoloLens 1, which also used LCOS, with Magic Leap 1 and Loomis waveguides. And so it kind of gives you two of these diffractive waveguides and then one of these reflective waveguides. One thing I will say is, I should point out, the Loomis is displaying almost twice the horizontal pixels. It has almost twice the horizontal and vertical resolution of the other two. So it's able to pass through a lot more resolution. Magic Leap had a lot of problems. Their image quality was pretty poor. Even HoloLens 1, the resolution was moderately okay, although like I say, it's half of what this is being pumped through Loomis. Still had a lot of color uniformity problems. This is kind of the classic of diffractive waveguides, is how do they control color? They can compensate for it, but you give up color depth, and even when you compensate, it's never going to be really perfect. Another way to go is really cheap. So we see a lot of these things where we have a large off-axis curved semi-mirror. One of the more successful variants right now is Mira. Mira just got in. It just got announced a few weeks ago that they're doing the Mario Kart. They're in the Mario Kart ride at Universal Studios Japan. I think it's going to be released, depending upon COVID, around February, they say. But you know, the advantage is it's cheap. You get a pretty good image. You get a large field of view. You get a large eye box. You got large eye relief. That's all good. That made it really good for building this. If you're going to put these out in a theme park or something, that worked really well. The downside is, and I'm showing this on an eyeglass, you can see how this is an uncorrected image. It's very well distorted. What may not be as obvious is you can maybe tell that it's in focus here and it's out of focus there. The reason for that is focus is also running out. So not only are you distorting the image, you're also distorting the focus as you run out. So, and you can't correct for focus. You do kind of rely on the eye to do it. If your eye is concentrated down here, you'll let the eye do it. There's also something kind of in between. Active Look, which is a part of micro OLED, has a thing where they're doing a similar thing, but on a kind of a small scale. And you guys may remember Meta 2, and I believe RealMax Quan, that's a fairly recent thing. It's also doing more or less this, although I think they're maybe a little bit different, but it's still an off-axis, very thin look. And as soon as you, and the reason why I brought this up first is because it's popular in some products, but also because it kind of sets up for bird bath optics. And we'll be talking about them in a minute. The main thing a bird bath does is gets away from this off-axis problem. It's going to put a beam splitter in there, which is a downside. The beauty of this is you go straight from the display back to the optics and back to the eye. Well, with bird bath, they're going to get a little more complicated. I'll show you how that works in a minute. But bird bath is still fairly inexpensive. You get very good image quality, particularly if you use OLED microdisplays, such as Sony's the most common one used today. You get no chrome aberrations because you're using a mirror, and mirrors don't tend to have colors spray out. So you get very good image quality. It's on axis, which gets rid of a lot of the distortion. It works with low brightness, Lambertian displays. Supports a reasonably wide field of view, but it does get bigger. The bigger the field of view, the bigger it gets. The cons is the form factor. When you look at this from the side, it's pretty thick, and most of the weight ends up out here. And then it's a little bit heavy, and the weight is put out way out on the nose. And one of the things is the further you get away from the head, as you move out the nose with weight, it tends to put more pressure and stuff and tends to outbalance things more. That's why if you go back and look at HoloLens, you'll notice they put basically a counterbalance. They put the entire compute pack behind the head, and that was to counterbalance the weight to the front. You tend to get poor light throughput. That's also kind of inherent in bird bath. Bird bath is far and away the most common optical structure I see used in AR, just all over. And then it becomes, bigger with bigger field of view. It also tends to require the projection engine to be above the glass. When we look at these things front on, you tend to see this big area on top of the glass, and you'll see that in Nreal as well. What's happening here is you have to put the light engine on top because it's still got to have it kind of comes down, hits it, and comes back. Now you can't put it to the side if you go small, but when the small, like Google Glass actually did a bird bath, but they did a small one and they could come from the side. But as soon as you want any kind of size, you end up having to put the bird bath, this bird bath structure. By the way, the reason why they call it the bird bath is you see light rays going in, hit the mirror, and it comes up, and people say this kind of looks like a bird bath. There are two flavors of bird bath. There's one bird bath that the display goes down, hits the mirror, comes up, hits the mirror a second time, and comes to the eye. And this is the one we're seeing more of, which is where you look through the curved mirror. You come down to the beam splitter, hit the curved mirror. The curved mirror is actually doing some stuff to focus and then sending it back to the eye. The problem you have, and the reason why it darkens so much, particularly with this curved mirror in front, is that you have to go through this curved partial mirror, through this beam splitter partial mirror to get to the eye. So it's got to go through 2 layers of optics blocking. Therefore, it tends to dim the real world a lot. You also, because it's making all these bounces, it tends to make the efficiency bad coming from the display. The display also loses a bit. Still, it's orders of magnitude more optically efficient. More of the light from the display by orders of magnitude of an OLED will make it to your eye than it can through, say, a pupil expanding waveguide that we talked about earlier. As I said, these come in 2 flavors. They have a bottom thing. Usually these are encased. When they do the bottom type thing, they're encased. They tend to be a little heavier. You only have to go through 1 layer of stuff. You don't have to go through this outer curve mirror, so they have some advantages. But most of what we see these days, like Lenovo just announced the Think Reality. By the way, the Think Reality is almost exactly an ODG R9. It looks strikingly similar, and that's probably not an accident. Nreal is also very similar optically to the old ODG R9 that came out about 3 or 4 years ago now. As I said, Nreal, this is from 2 years ago, 2018. So the image quality is absolutely beautiful in terms of you're basically looking at a mirror image of an OLED display. There are a few problems. You do get some secondary reflections as the light bounces around in here. Each of these surfaces, there's some opportunity for some ghosting, and you do see some ghosting in it. But compared to any other AR display, this thing looks quite good, and this is why you'll see people kind of heading that way when they want to get something. It's also very simple and fairly cheap, but it has the downside of you're going to block about 70% of the light. When you look through it, it's a lot, you lose a lot of light. The other thing we have in all of AR is that your background, your black, is whatever you see. So if you're looking at white concrete, you're looking at something that's pretty darn white. If you're outdoors, white concrete, 10,000 nits. If I took this Nreal headset outdoors in sunlight, you wouldn't see anything. It would just, all you would see is the white concrete. You just have, only thing you know that you're wearing the Nreal is you've blocked 70% of the light, so it'll be 70% darker. But still, even if you take 10,000 times 0.7 or times 0.3, you're at 3,000 nits, and this thing is probably getting to your eye a few hundred nits. I'd like to bring up one here. This is a small startup out of Israel that I'm quite fond of the basic concept of this. I like it because it's simple. It's a small company called Arim, and it's what I call super slanted. That's not their name for it. It's just kind of my generic naming of what it is. But what they've done is they've taken the prisms and the beam splitters and stuff like that and put them at this super slanted angle, a very heavily slanted angle. And by doing that, they're still able to optically get you effectively a mirror reflection. And so it looks really, really good. But we still have the problem that because there's no power in it, one thing that happens with this mirror is you're actually magnifying the image. The mirror is making the image bigger. When you do something like this, you don't have any magnification coming through here. So all the magnification has to be provided by your original projector optics. So whatever is taking your display, you've got to have the lenses. So your image out here can't be any bigger than the image up here. And actually it's by that distance away. Also, it has a fairly straight path. So it can't be done as flexibly. Another one that gets used quite a bit, this has been used mostly in military so far that I know of. For example, SA Photonics is a free-form optics. And basically it's simple, it's easily rugged, real good efficiency. The problem is that optically what they want to do, if you did a free-form that you didn't see through, you don't need a corrector. But if you do a micro display into the eye, you have this kind of curved surface here that's also magnifying. Because of these two surfaces and all, you can correct most of the distortion. The problem you have is that you have to put a corrector on, because if you look through a thick piece of glass that's wedge shaped like this, you'd get a very distorted view through it. So what they then do is put a free-form corrector on, and you kind of see that all here. You've got the lens, you got the corrector. So what happens is you're now looking through an even thicker piece of glass. And that tends to be the downside to it. It gets kind of very big and bulky if you go to very high resolution. This makes a little more sense if you're looking at doing VR than AR, because you don't have to have the corrector thing. Another variant of freeform is a company called Twos. They basically built freeform into prescription glasses. And they've been at this. They're formerly Zeiss. As a matter of fact, a few years ago, there was some noise about maybe them working with Apple. As far as I know, that noise has died down. But they've kept on with it. Twos spun out of Zeiss. But it's basically a small freeform plus a Fresnel mirror that kind of redirects the light towards the eye. This is from their patent. This is from, actually, I think, this from the patent. This from from Kress's book again. But basically, they're allowed to route light into the eye. They get a relatively small image, and the image can't be in the center. This Fresnel lens does cause some distortion. Usually, it's right out, just out of the center of view, not very far, but just out. You also get a fairly small eye box, but not bad. It's workable. Generally, in this optic design, and this is quoting from Kress's book, you're limited to about 25 degrees. So it's a fairly small field of view. Another thing that gets a lot of talk, Google just bought out what was left of North. Bosch has been working on this. What they're looking at is a direct laser scanning off a holographic mirror. What the holographic mirror does is you can build a flat surface or even a slightly curved surface. But if you just metal coated this thing like a mirror and shot lasers at it, the lasers would miss your eye, because the curvature of this thing, and you sometimes will see these things, and actually there's a C-Reel just has a product where they have this extreme curvature. But if you curve it like normal glasses or normal eye protection, the light will miss your eye. Well, what the hologram's able to do is effectively, particularly with narrowband light, it's from lasers, it's able to redirect that light as if the mirror was tilted. So even though the mirror, so instead of getting a mirror reflection, you get this kind of, you basically build a holographic mirror that bends the light more towards the eye. The downside of this, and you can see here, like in the Bosch booth, they're having to align this thing to your eye. So they have a whole fitting process, and North had a fitting process. They have a really, really tiny eye box. Effectively, the eye box is as big as your eye. Now, North did a replication of it to try to create a little bigger eye box and whatnot, but it didn't work so well. Anyway, it's very small, very light form factor, but the tiny eye box, the tiny field of view, the image quality is generally not all that great. So it's really limited to like what I'll call data snacking, and even then fairly limited data snacking. Another one that gets talked a lot about, and I'm not going to hit this one briefly, is a pin mirror. The idea of a pin mirror is you have these little tiny mirrors in here, and effectively you get what they call a pinhole effect. And because of that, it tends to, you're basically rejecting the out of focus light rays with this. It sounds good, but you're also rejecting a lot of light. So you do get a very high depth of field and depth of focus. That's true. But you do get hopping, what I call hopping. You kind of see here how the image kind of goes in and out. You get kind of dark spots. It's got this issue, and they're working on it, but it's not clear that you can make that. It's not clear to me yet that you can come up with a mirror size and a pin spacing, because you'll see like on the lower resolution ones, they tended to use larger mirrors and fewer of them. For the higher resolution, they went with a large arrays of tiny mirrors. This is the large array of tiny mirror version. You still get a lot of this hopping effect from things to things. So we'll see if that works out. The other one that's talked a lot about is pass-through VR. And I put this up here mostly because of some talk that Apple might be doing this. with pass-through VR, pass-through AR, which is VR plus a camera over each eye, the virtual image quality is great. If you use OLEDs, they can be plenty bright. You're not trying to compete with the real world light. You got hard edge occlusion, or the ability on a pixel level to block, the real world is trivial. The computer that's in the headset just decides what to block. You need lower brightness of the eye, so you're not overtaxing the eye. The power efficiency is going to be great because you're not competing with the real world. And it's going to be much lower cost for the same resolution and field of view, perhaps an order of magnitude less, if you try to get everything to equal. The cons, you're visually isolated, which is dangerous in the real world. You have latency. You have focus. It doesn't focus like the real world. I don't know if they're going to do variable focus or what, but you're looking at a display. You're not looking at the real world. It doesn't. In the real world, we have infinite levels of focus. Everything at different distances focuses differently. Whereas in this headset, things are going to tend to focus at a given distance. Now you could talk about doing something like a light field inside this headset, kind of following on from the prior talk. You could try to do a light field, but it becomes highly impractical. You're going to do a real-time light field. What's going to happen to the latency and whatnot? It's just highly impractical. So the dynamic range is less in the real world. And there are all kinds of social issues. Do you really want to be talking to somebody who looks like the headset? Generally, the rule of thumb is that what's hard with optical AR is easy with pass-through AR, and vice versa. In other words, things that are easy in one are hard in the other, and hard in one are easy in the other. Let's talk about display devices. The most common display device used today is field sequential color. That may be changing, but that's the one that's been up until this year the most common one. It's basically the lowest cost micro display for any kind of resolution. The panel itself is low power, lots of pixel size, many suppliers. The other thing, it kind of cheats on étendue because the size of the light source is what drives the étendue, and the size could be a small LED. This is why you're able to deliver more than 3,000 nits to the eye, even with waveguides using LCOS. It's because the light is small. The cons are the illumination path. You have to illuminate these things, and that can cause issues. The uniformity tends to fall off. It requires polarized light. So right off the top, you lose 60%. It's not as bad as it seems sometimes in near eye displays, because oftentimes they use polarizing optics. It's more efficient in a bird bath, for example. And then you have field sequential color, which is a big issue. It breaks up. That can be a real problem for people when you move your head. Very common, people who used HoloLens 1, if you moved your head around, you noticed how you saw it. Now, they used a really slow field sequence rate on the HoloLens 1, and so it made it really bad. But it can be faster. There's some LCOSs now that are faster, such as Compound Photonics is claiming a very high rate. There's latency with the field sequential because you got to kind of build up the color and display it. Once again, Compound Photonics is working on something to address that. But it'll always be some more latency than you would have with a non-field sequential display. And there tends to be a little bit lower contrast. I'm not going to talk much about DMD. DMD seems to be kind of fading in AR. I think they have some real advantages in non-AR markets, non-headset markets, but I don't see them getting used a lot. And even some of the stalwarts, such as DigiLens and Wave Optics, that were almost exclusively DMD, have been moving to LCOS. So I get the sense that there's a thing. And the problem is that when we build these really, really tiny displays, LCOS is flat and planar. The mirrors that they use are built on top of the silicon, whereas with DMD, they move. And because of that, there tends to be more gaps, and that all translates into bad things like diffraction and whatnot. And it's just LCOS is a lot less expensive to make, particularly at higher resolution. So all those things tend to work in its favor. DLP still has advantages. The one company I know using that's been using DLP lately is C-Reel. C-Reel's doing once again a light field type device, and they are using the very fast switching mirrors to help with DLP to help them accomplish that. Like I say, it's brighter, tends to be brighter, but generally the power consumption up front tends to be more of a disadvantage than the advantages they get from, say, not requiring polarized light until you get to really, really bright images. As I said, the Étendue is controlled, like here's the Loomis engine. They have a really small LED that tends to control it. There's a Loomis clone, kind of shows the path that the LED is much smaller than the display. At one time, I thought Apple was maybe going to use LCOS with using their Iconia stuff. There's some Iconia patents on showing how to reduce. Traditional beam splitters are very thick, and this is really bad optically. This creates all kinds of problems with a thick beam splitter called what's known as a working distance. Makes it much harder to build the projection engine and whatnot. Iconia, which is owned by Apple now, they had a way to have a fairly slanted thing. And Hymax also does a thing with light guides. So there are some tricks to do there. And I'll talk a little bit later. There's a thing by DigiLens. Here we go. DigiLens actually has got a new thing called their they got their new product that they're talking about. They've got actually some working samples now that has about only a 3 cc engine for 50 to 70 degree field of view. It uses 3 lasers, and kind of in reverse, it's using the waveguides to route the light from the lasers to the LCOS and combine them and get it out. So they get a very, very thin optical path there. Compound photonics, interestingly, this appears to be a compound photonics panel they're using. Compound photonics put out their own 3 cc, much more conventional engine, although they're doing some trickiness to pack it all together. You can see how the DLP engine's a lot bigger. These are roughly to scale. Now, lasers in theory are small. Laser beam scanning that was used, say, on HoloLens 2, but actually, because of all the conditioning and ways in which they have to manipulate the light, they actually end up with a fairly large light engine. The optical engine is actually quite large. It's several times the volume of any of these other engines. Oh, and then we have kind of foreshadowing here, going to micro LEDs. They end up with really tiny engines because they don't have to do this illumination path. The illumination path is generally about 2/3 of the engine. So if you eliminate the illumination path, you can get a really tiny light engine with these things. But as I said before, both of these are using waveguides. I wonder about the efficiency, in-to-out efficiency getting through here. Don't think I'll talk too much about field sequential color today. I wanted to I've done a lot of studies, and look at my weight. I've got a lot of this on my blog. I've gone into great depth on how HoloLens works, how it scans. It's a messy process, and it's really poor image quality. Anyway, any realistic way you want to measure it. And I stand behind the fact that I think I've taken some of the best quality images and most representative to the eye images that I've seen anywhere ever taken of HoloLens. I didn't just stick a cell phone. You're not going to get a good image of HoloLens just sticking a cell phone in front of it. I went through a lot of work to position it properly, use good cameras and all that. But this is interesting. If we actually look at HoloLens 2 from HoloLens 1, this is a HoloLens 2. The actual resolution of HoloLens 2 is much worse. Even though they claim it's higher, it's not. If you go out and measure it any way you measure it, or if you take a human and take a HoloLens 1 and a HoloLens 2 and swap them, like put one on and swap them, it's immediately obvious that the HoloLens 1 is vastly higher in resolution than it. And I've detailed this a lot on my website. So I suggest you go to my website, and you'll find and look up for HoloLens 2, and there's all kinds of information on it out there. only thing I want to say here is right now, if you think about LCOS separates the light generation, the LED, from the LCOS device, from the display device. In the case of an OLED or a micro LED, the display device has to generate the light as well as control the light. Because of that, you're now running the light or running the power into the thing. So now you have to have a more complicated pixel, and the pixel has to have structure in it capable of handling current. In the case of LCOS, it's static. You're just driving you take an electric field, it's basically a capacitor. You drive an electric field and you make the liquid crystal work. So that's the key point here. Oh, one other thing. Because LCOS is field sequential color, you only need one of them. Whereas if you're going to go with a micro LED, if you want a panel, if you want all of the colors on one panel, you got to put 3 sets. So it's more complicated and you need 3 of them. So that's one of the reasons why OLEDs and micro LEDs are a lot more expensive than, say, LCOS is. Like I say, micro OLEDs, very, very common in low cost, high quality type images. To get a low cost, high quality image has drawbacks, but it's going to give you the best image quality of any of the headsets I've seen today. Better than every other technology. It's better than even micro LEDs today, and I'll talk some about why. Extremely high contrast, it's self-illumination, so it leads to a fairly small size. All that. The downside is it's what we call Lambertian light. It's like that, remember my spray pattern of the light. It's spraying light everywhere. It's going to get you maybe 3,000 nits today. By the way, most of the OLEDs you buy are less than 1,000 nits. So the high brightness ones are maybe 3,000 nits today. The super high brightness ones coming out might get you to 7,000 nits. This is ridiculously too low to go into a pupil expanding waveguide. You'd get maybe a nit out, so you'd barely be able to see it in a dark room. Like I say, Copen and Imagine are promising 30K in 2 to 3 years, but that's still not enough to go into a pupil expanding waveguide. So it's much lower nits. There are burn-in lifetime issues, just like you hear about with televisions and whatnot. It's higher cost. It's generally lower resolution than you can get LCOS at because they're going field sequential color. These guys, if they're going to put 3 pixels, so this guy only has to put 1 mirror down there and sequence the light, so he can generally get higher resolution in the same size. And as I said, it's Lambertian light. The big talk is micro LEDs. And this seemed to be the Valhalla thing. You heard all these people talking about 1 million nits and 5 million nits. And when I first heard about it, I thought, well, man, we have 5 million nits. We can drive anything. But you got to look a little more carefully. It's good. It allows for things. But so it's millions versus thousands. Compared to an OLED, it's millions versus thousands of nits. So it's about 1,000 times brighter, potentially. It's better energy conversion efficiency, better fill factor. And this isn't an exact number, but from what I've been able to gather, it's about 10x more nits per watt. So then you might say, how do you get the extra 1,000? So you went from, if you think about it, if it's 1,000 times more nits, then 10x, where do you get the other 100? Well, you get the other 100 by driving it harder. The big part about it is that you can drive these LEDs a lot harder than you can do OLEDs before they burn up. So you have a smaller emitter, which means you get better étendue. They get more leverage out of small micro optics. They even build optics into the structure of the LEDs themselves on some companies. So it's orders of magnitude faster switching, which means you can start doing some neat stuff. Like talked about DLP earlier. DLP was they can switch fast. That's where C-Real was able to do a light field. Well, if you have micro LEDs and you can control them, then in theory you could do all kinds of neat stuff. They can be driven much harder, and that's much of their brightness advantage over OLEDs. They can be driven hard. They're about 10x more efficient, but like I say, a lot of that's coming from there. It's narrower spectrum, which can be an advantage with some filters and stuff. And then you've got so much going on in LED manufacturing. The con is it still has eton-du issues with waveguide. This is the big conundrum today that I see when I talk to the real experts in optics. Is the conundrum is it's still got an eton-du problem with respect to waveguides. It will work, but it's not very efficient. Now, it does have the advantage, and so does OLEDs, that when if you're not driving a pixel, you're not consuming power with it. It's very efficient. Whereas LCOS, you illuminate the whole thing. If you put up black, then the LCOS is just blocking all the light. Here, you don't block light, you emit it. And so if you're not emitting light, it's fairly efficient. If we look at most AR applications, they should be sparse. We're not trying to put a movie up there. You're trying to draw on the real world with something. So as long as you're providing sparse information, then you can kind of deal with this power inefficiency, so long as you're not trying to do too much. But it's high cost and very low yield to date. It's very poor pixel-to-pixel brightness uniformity. You're not going to want to watch a movie on it anytime soon. It's really more for this sparse data. Right now, the ones who are like Jaybird is going to production, they have high nits, more than 1 million, but it's only a single color. Or you could do 3 chips, and this is being shown by, for example, Guttag. 3 chips with waveguides are possible. A Stendo has RGB, but it's lower nits. And in Stendos, I've seen working units. So they do have full color. This is kind of the space. We have Plessy, who was just bought. Plessy was, of course, bought by Facebook early this year, basically right after CES last year. Stendo has figured out how to do full color on a backplane. Compound Photonics, who was working with Plessy, has gone out on their own, and they're doing their own micro LED, working with partners to do the LED portion. Jaybird is probably the guy closest to production. You can go buy samples from them, and they're announced that they're going to have samples in production later this year. But it's a complicated process. You got to build a silicon backplane wafer. You got to flip the LED. You got to build the LED separately, flip it on it, get it to bond, get it to yield. Glow's been around doing stuff. Vuzix was, we'll talk a little more about them in a minute, but Vuzix has announced that they're getting ready to go to market with some new glasses with a waveguide. Very, very small and tiny. Basically, this is a variant of it. This is where they were a year ago. They're in the process of productizing this into a product. This is what I wanted to show you, though. This is from Plessy. I shot this with literally handheld. I was surprised it came out as well. But this is a photo micrograph I shot of Plessy at last year's CES. And what I want to do is blow up this one region. And what you see is I was able to find the original source material. And you see the original source material is very smooth, particularly in this area. But it's very grainy in the image I took. And the reason why is that all of them, and I see the same thing in Jasper, I've seen the same in every micro LED I've seen with my own eyes. It's always kind of grainy looking. And the reason why is that the brightness is varying dramatically from LED to LED. And I don't know if this is part of the process, part of the transfer, what. But these aren't just dead pixels. You will find dead pixels if you look enough in these too. But these are all prototypes. So that's not, that we're at that stage. But it's still very grainy. I think that's going to be a bigger problem. You're not going to want to watch movies on them, but this is probably acceptable if once again, you're trying to point out things in the real world. Plus, Facebook has been on a spending spree. They bought, a few years ago, they bought InfiniLED, and they didn't exactly buy Plessy, but they locked them up. They've locked up all of Plessi's ability to sell micro LEDs, at least to the display market. Remember I talked about earlier that they're building structure into the stuff. So they actually built a mirror in InfiniLED. What they were doing is building structure into the silicon substrate to build these little mirrors. This is all about collimation of the light, trying to get the nits up for the given amount of light that's emitted. These are some pictures from last year at CES. So this is about a year old. This is a Jaybird fine line drawing. I wouldn't take, they've had some electronic bugs, but that's once again expected. They're showing early prototypes. That's not a real problem. That's a temporary problem that's going away. They also showed with wave optics at the show, they showed their micro OLEDs working with the wave optics. Once again, if we look at these things really close up, you see it's kind of grainy looking. If you look over here, this is even a closer look up at a blue one. You see how it's real grainy looking. That's where they're at with LEDs. They have a huge amount of variation from pixel to pixel. The one guy out there who can do full color, and I have seen it a few times, is Stendo. Stendo is a little company down in Carlsbad. And they've been at it for a lot of years, but they're the only guy I know of who's got really what I'll call a monolithic full color process. Instead of having the pixels side by side, they literally can stack them on top of each other. They put micro optics on top to help collimate and polarize the light. And so they've got this thing they call a stacked pixel. So they're the only guy I know of right now who has a single chip full color one. It's fairly low resolution, it's lower brightness, but they are the only one with a micro LED with full color. Yeah, just to hit a few things here. Vuzix, this is from a Vuzix video. They're talking about doing monochrome green. I have not been told, but it doesn't take a tea leaf reader to figure out they're probably using Jaybird. They're also looking at doing, they showed in their video a color one where they throw 3 stacks. I think what they're doing is they're probably taking 3 waveguides. This is what DigiLens did with their Wild and their laser. You basically take 3 waveguides, only they're going to be imaging waveguides. So what they're going to do is it's kind of like the reverse of what DigiLens did. And they're going to take 3 waveguides and bring the red, green, and blue in. And by the way, that's what Magic Leap did. Magic Leap's were spatially separate. Their red, green, and blue came into their 3 waveguides in separate places. So that basically you just bring the image in 3 separate places and combine it in the waveguide. I have a saying in this industry, if you can think of it, Facebook's already tried it. And I think that's pretty well true. Almost every time I see a new concept, I can go digging for it and find out where Facebook wrote a paper about it or where Facebook filed a patent on it. So real quickly wrapping up, and I'll those who've got YouTube and all can pick this up. It's also on my website. I've been trying to map out how the world of AR displays maps onto the optics. So basically what I say is various optic solutions map onto various different types of optics. So over here we have our optics, over here we have our display devices. And kind of, this is one of the big factors today, is can you get micro LEDs to map well onto diffractive? There are issues, mainly this étendu issue. So diffractive waveguides have bad color. We're waiting to see if reflective waveguides can work well or can be cost effective and manufactured cheaply. We have holographic reflectors, which I just don't believe that's a very good way to go myself. Freeform optics has a lot to say if the image resolution is small, particularly if we're talking twos. Within freeform, you have things like twos. And twos has shown that they could do something if you're willing to do, if what your task needs not a lot of data. I'm actually kind of excited about this rim super slanted that I've talked about. And then there's other things you can do, but most of the attention is going up here. and a lot with birdbath with either micro LED or micro OLED. Right now, the hottest thing probably is here, and I'll talk about why in a minute. There's three guys in the what I call the billions per year club. You got Facebook. They've got a huge team of smart people working on this. And as I said before, if in AR, if you can dream of it, Facebook has tried it. Apple, if you just by searching around and looking at papers and looking at patents, you can't see Apple putting in the half or a tenth the level of effort of Facebook. Now, maybe they're doing it. Maybe they're keeping it quiet. Maybe they're working through shell companies they bought. For example, Iconia still files patents as Iconia. They don't file patents as Apple. So it gets a little harder to follow the paper trail on Apple than it is, say, on Facebook, who's got this major facilities and lots of people and publishing excellent papers and with some of the biggest names in the industry. Apple, multiple reports are using Sony micro LEDs. At first, I thought they might be using Iconia, which is something they bought. But if true, Apple's is not using a classical waveguide. They cannot be using Iconia. So by process of elimination, you say, well, if it's pass-through AR, super slanted might be a possibility. They might go pass-through. They might do something like a rim, or they might go birdbath. But birdbath doesn't, that's like basically going to look like Nreal, or going to look like ODGR9, going to look like everybody else. That doesn't feel very Apple-like to me. Robert Scoble on the AR show, give a plug for that. That's an excellent show, by the way. Jason McDowell does a great job with that. Asks great questions. I was on, I think, his second or third show. I think he broke it into 2 parts. So there's like 3 or 4 hours of me talking if you want to hear more. But Robert Scoble, who's kind of, I'll call an industry gadfly, but he was very famous in the days of Google Glass and whatnot. He was just interviewed a week or so ago, or just published a week or so ago on the AR show, said that Apple is using pass-through AR with a flip-up screen. It's plausible, definitely plausible, but man, I once again have a hard time seeing how that works. And I sometimes think that they're going to delay and then claim it was due to the pandemic. I just, and then Microsoft has so far retreated to the existing market of enterprise. There is a real enterprise market. Microsoft's exploiting that right now. There are things there where if a guy, you can save a guy, you can say, you're paying this guy, fully loaded guy working on a factory floor, probably over $100,000 a year. If you look at salary, benefits, equipment cost of facilities, all that stuff, you're probably costing more than $100,000 a person. You sit there and say, hey, if I can save you just a few percent of his time, it pays for itself. And that's the argument that wins the day right now in AR. That's why I think where Microsoft's having success. The image quality sucks. It absolutely does. By any rational measure, it's a crappy image. But it's linked to the real world. It puts a spot on a thing in the real world that says, tighten screw here or whatever. So the real thing is being made not by putting out great movies, not by the things you see in Iron Man and all the movies. It's being made by people who are basically saying, this is what AR lets us do today, accept it, and then say, what could be useful by this? Like I often say, if AR would, if all AR took was money and smart people, it would be here already. And I think, like I say, Google found that out. I think that's it. I'm sorry. I know I ran a lot longer, but hopefully it was good content. That's it for me. I don't know if we have time for questions or not.
Thanks, Karl. Let's just do a couple of questions from the feed.
Yeah, so I can post that question on a Zoom chat so you can select which one do you want to answer.
Okay.
Because there's a few of them very good.
Okay. If I can get to that.
It's all on the Zoom chat.
Yeah, I have to close down my share window to see the Zoom chat, as far as I know. Okay. Okay, I see one question is, what's my thought on micro LED from Jaybird? they're there, they're available, they're not perfect. Driving them is kind of tricky. I don't know that they're really a tie-up with Vuzix. I think that's just more a partnership of convenience. I mean, I'm pretty sure Vuzix has been providing their development kit waveguides. If you look at it, it looks exactly like what they showed at CES. So, but I don't think there's anything really special. And then the other question was the AR system from Karl. Well, I hit on some of that with the pin mirror stuff. I've run that up the flagpole. The idea of a scanning, like micro LED scanning, I don't think they're going to get it to work. In my personal opinion, they might, but I think they're going to have a hard time. And I've talked to people in the industry about this idea of scanning a linear array or a kind of a two-dimensional array that you scan to make it do even more resolution. And you have some subarray, say 1/10 of the pixels, and then you scan it around and all. And everyone's pretty skeptical about it, that they'll get that to work. And then the question is, will it be bright enough when you do all that? I was intrigued by it at first, but the more I run that up the flagpole, the less. The C-Real Light Field display showed at CES this year. I haven't seen the very latest one. I know they were using DLP. I've studied. They actually have an excellent patent. If you look it up on free patents online, you can look up their patent and it explains how it works. It's actually a really fun read. The patent's excellently written. I'm still a bit skeptical they're going to be able to get it to reduce to the form factor they want. It feels to me like they need micro LEDs to even make that happen, because they need the time sequence. They're basically using time sequential, whereas you did spatial with the Leah and did spatial. They're doing it time sequential to get the light fields up there. And they've got a tricky thing with how they illuminate. They're basically illuminating the LED. How they're going to make that work if they switch, say, someday to micro LEDs, they've got the speed, but now they've got to do something to make the light come from different angles and directions. So I'm a little skeptical on it. They're smart guys. They're nice guys. And I wish them well. But I think it's going to be harder than they think to get that reduced to the form factors that they're showing. What's the requirement of display? You know, it's really the character light. You really kind of want for these waveguides. I mean, they're going to lose a lot of nits. So you're looking at needing like 1 million plus nits into the waveguide. And it really depends on the character of the nits and will it fit in the hole. You got to talk this Etandu thing, which is really complicated. But you've got to be able to get not only collimated light, but you got to get it to fit into the entrance area of these waveguides. And then we get back to, well, diffractive waveguides have really bad color control. So you still get a pretty crappy image. So it's really tough going that way to get there. That's why I kind of like, I like that super slant from RIM a lot, because it's got the, it's more optically pure. It's optically simple. It has issues too with how you're going to get the image big enough. So there's a field of view issue. Yeah, the main difference between a RIM and Loomis. Loomis has pupil expansion, so their reflectors are actually all reflecting the same image in multiple places. With a RIM, the waveguide is much more slant, or the mirror is much more slanted, and there's only one mirror. So in one case you have multiple mirrors, each kind of having copies of the whole image that you see in it. So when your eye moves, you see the whole thing. With a RIM, the image is coming in, not collimated. You're getting a more diffuse image. So like a RIM can work with OLEDs, and they are working with OLEDs. You could never use an OLED into a Loomis. There are different pros and cons and take a long time to explain. Let's see, what solution is best you settle? Well, there's no best. I like that RIM thing a lot right now. TUS is pretty good TUS is good if you need to do like data snacking, because it's all form factor, very rugged. I mean, one of the things I like about TUS is really rugged form factor. And you've got a big name, they're working with Zeiss, and so they got a big name company behind it and all. So there's a lot to be said there. I'm not real big on the laser scanning off, ricocheting off a hologram, because the eye box is so tiny, it's a problem. Let's see, other things. I hope I hit most of these. Yeah, I say it has low nits. I don't know their exact number for a stendo on their nits. They're claiming hundreds of thousands of nits. I don't think they're delivering that today. I think they're delivering in maybe the 10,000, maybe 20,000 nit range, which is way beyond where OLEDs can actually deliver, but they're not nearly as bright as the others. The stacking structure, I think, makes it difficult to do that. They're definitely aiming, they can't be aiming at waveguides. They've got to be going for non-pupil expanding. When I say waveguides, actually, a rim is a kind of waveguide by what people call waveguides today. Really what I mean, usually when I say waveguides, I'm really saying pupil expanding waveguides. You just can't do the pupil expansion. You have this étendue loss followed by the pupil expansion loss. And when you do that, nothing comes out. You basically have thinned it out to the point that you can barely see it. It's like looking at the sun from planet Pluto or something. Let's see what else. You mentioned a variety of issues with the HoloLens 2. They were plagued by quality issues. Tried one recently, and none of the original, I'm sorry, I should read these. It had none of the original color fringing and focus issues or light bleed issues I saw in the original one. Okay, so you felt like it was slightly better than Magic Leap. I know they've been working on it. I heard they did something that some people say hurt the resolution a bit, but made the color rainbowing less. Fundamentally, the laser scanner, even under the most ideal conditions, is like a quarter of the resolution they claim for that thing. I mean, there's no way they're using two lasers. I know how they're scanning it. Like I say, go to my blog, it's not there. I do hear that they are improving it. I heard that there's really severe criticality in how the lasers and the alignment and the placement and everything is. It's like super critical. And that's why they had such huge variation initially. And apparently they're locking that down. They've done something with some kind of filtering or some kind of changes to the waveguides that apparently has improved the rainbowing colors a lot. But when they're all done, they still going to have the scan rate of the HoloLens 2 is way too low for the resolution they're claiming. I mean, that's a fact, and I'll go to court on that. Okay, that the resolution is far too low for the resolution they're claiming. Therefore, the display flickers, the text flickers. Text is going to be a problem forever. I grew up in I started in the display industry really in '77. I worked on a video game chip, and I've been dealing with televisions and flicker. In the 80s, late 80s and 90s, they made it illegal, basically in Europe. They passed standards that said you couldn't flicker as bad as what HoloLens does today. Their scanning speed is just way too low. So it's got its pros and cons. It's still kind of the winning there because in the land of the blind, the one-eyed man is king, so to speak. They did do one thing. I do like they did say, forget image quality, forget a lot of things, but let's focus on making it comfortable. Let's lock it to the real world. Let's get something out in the market. They give good eye relief, which is hard to do, so that you can wear it with glasses. They have one of the more practical products out there. And I think that leads a lot. So they did a lot of things, but the display I still think is really pretty poor. Fortunately for them, and what they realized is that you really don't need a very good display. You talk about it, you market it like it has a great display, but it's kind of emperor's new clothes. If you really know anything about displays, it's a horrible display. Mojo Vision. That's a good one. Yeah, there's some basic physics problems with Mojo Vision. What they're doing is they're basically building, if you know a telescope, how a telescope works with a mirror, they're building a sub-miniature telescope in reverse in front of your eye. The problem is, and it's actually very related to the Letten AR problem of the pinhole. If you're going to put this right in front of your pupil, it's going to disturb the view of the real world because the light, a lens is collecting light. And what happens is it's taking light from a patch in the real world and focusing it onto your retina. Well, you've just put a dot, if it's aimed right in your eye, you just put a dot blocking out the nice, easy, good, solid rays. And the only rays that are going to make it to your eye are those outer rays, which are harder to focus. So you're going to hurt the image in the real world. there's also a limit to how small they can make the pixels. The wavelength of light, like green is 530-ish nanometers. They can only put so many pixels up there before that thing gets so big that you can't even see out. So it's going to be, for at best, very limited data snacking. Yeah, I could see it for spy work and maybe a few military things, but it's never going to be a consumer-y thing. And there's other issues too, but I'm pretty good. Yeah, as I said at the beginning, people like reading my blog when it's not about them, because I tend, as an engineer, I'm very analytical, and I tend to find the faults in things. So there probably are some good things about all this too, but I tend to find the faults. So I think we've answered a lot of questions. I don't know if I don't know anything about Magic Leap 2 coming this year. What's kind of thought of micro LEDs from Dave Bradley? I think we've hit almost all the questions. So,
yeah, thanks, Karl. You did a fantastic job, and thanks for answering all the questions as well. There's a few other events coming up, which the audience might be interested in. Sasha, would you mind sharing a couple of those?
Right. So if you want to so we actually please follow us on the Facebook group. We're actually posting like different types AR VR events, not only our groups, but it's other coming the workshops, events. So please following. And yeah, Karl, the presentation was awesome. To be honest, I learned a lot, like insanely.
Thanks.
And what are the best way to contact with you? Because I saw you posted website, and what is the best way?
I did give my direct email, but you can get to me through the website, particularly through the comment section. If you're a first-time visitor, it shouldn't post if you tell me, hey, don't even print this. So you can go through my website, or you can go directly to Karl, which with a K, at KGOnTech.com, KGOnTech.com. Either one of those two will get to me. If you look at the name of the blog, it's KGOnTech. I made a really silly mistake early on in starting the blog, like over 9 years ago. Otherwise, the name of the blog would have been KGOnTech or the web address. So I hate to do the consolidation. I guess at some point I ought to get those two to merge. So, okay.
Thanks. And yeah, thank you so much, Karl and Nima, for your presentations. These were terrific. And
Thank you for having me.
guys, I'm really blown away by the turnout we had today. And sorry about the technical issues we had earlier on. So we're going to be looking at some different approaches for the future meetups. And but I'm really excited about what we have lying ahead for us this year. So, and thanks, Sasha, for organizing the questions and the Facebook post and everything else. So. Well, take care, everyone, and have a great rest of your day.
Yeah.
Thank you.